Okay, welcome to a new Python tutorial. After we have already discussed many of these built-in functions in Python, I would like to go now more into details regarding certain packages or modules that are included in Python. And one of them, which I think is one of the most powerful ones and which you maybe use quite often, especially when you work in science, is called NumPy. And this stands for Numerical Python. It's a very powerful package, as I said. You can do many things related to matrix manipulation, linear algebra. It also includes a lot of functions which are important, like for example Fourier transform you can do with that. And now you will see that that many things which you do normally with lists in Python you can do with NumPy much faster. In general, you can also say it's much more performant than the built-in lists or arrays in Python. So it increases the computation time by some factors, and also the memory consumption is much lower. So in this case, we will just directly, as usual, dive into the topic. So I created here a new Python file which I call num.py, and now we import our NumPy module. Usually I'm doing this as NP, so now we can easily refer to that. Okay, and first in the first part I would like to explain how you can actually create an array in NumPy. And for that, first maybe we create just a simple Python list, as we have done this several times before, and we can just insert maybe some random values here, only just for checking how it works. Okay, and now we can write np.array, so the function which we use from this NumPy module is called array, and then we have to insert our list here. And and to check whether it works, we can just print out, we also have to give, of course, a name to that object, so let's call it maybe just R for array. And now we can print out our object, our variable that we created, more or less. And then you can see now here we have this content of the array. So this is not so much interesting so far, but later you will see what kind of nice things you can do with that. What you can also do, you can print out the type of that, as we have done this also several times before. And now you see that it's not a list anymore, it's now a NumPy ND array for n-dimensional. So later I will also show you how you can create multi-dimensional arrays. So but here in this case I want to just emphasize on the fact that this is not a NumPy tutorial. I just want to give you an overview what you can do with this package. But in order to really go deep into this, I would need more time. Maybe if you are interested, you can write it into the comment section that maybe you want to have a further tutorial in the future. Maybe I should go, or even making a full lecture series about that, so you can learn everything which is related to NumPy. But here, this is just meant as an overview, so you get an idea what you can do with this package, and to maybe go yourself a little bit deeper into that. What I want to show you also is that you can easily plot these kind of arrays that you create. So we create again matplotlib pyplot splt, as we have done it before, and I also have a full lecture series about pyplot. You can check this on my YouTube channel. And then you can write just plt.plot, and then we insert just our array here. And then we don't want to show that, but we want to save this figure, so let's call it maybe r.png, and when we run now our code here, you see now we get here our picture r.png, and what it does is just incrementing the integer on the x-axis from 0 upwards, and on the y-axis it shows the values of the array. So very simple. I mean, this is very nice if you want to do some data analysis, for example, just to show how it works. But now the real strength of NumPy will come now. So let's suppose we just overwrite this array that we created, and we want to multiply all items with 5 and add maybe just some offset to that, for example 10. And now we print this out. and see what now is shown in the terminal. Yeah, you can see now that 5 is multiplied by 5 gives 25, and then plus 10 gives 35, and so on. You can do this for all items, and what it just does, as I said, is taking every item, multiplies 5 with this, and then adds an offset of 10. And if you want to do this with Python lists, you have to either write your own function to do that, or you have to always loop over all the entries, and this is much faster way to write it, and as I said, much more performant. So you can if you measure now the time, if you insert a timer and really check this out, maybe then you should get a factor of maybe 2, 3, or 4 increase in the performance. Okay, what we can also do, we can easily create arrays. So let's suppose we want to create an array from 1 to 10 in certain steps. So there are 2 functions in NumPy which you can use. So let's call this array maybe R2, and we can write here NP. One of these 2 functions is called a range, and it needs, of course, a start point, it needs an end point, so in this case 1 and 10, and it needs the step size. So let's suppose if we write here 0.5 and we print out our array R2, you can see now we get an entry 1.0, 1.5, 2.0, 2.5, and so on. So it just creates an array between 1 and 10 in 0.5 steps. In principle, it's very simple. Now we have here floating type. So what we can do, we can also change the type of that. So for example, here another parameter which we can hand over is called dtype, and this is a NumPy built-in variable, you can say, parameter, and you can then define here what kind of type you want to have of that array. And when you run this, then you can see that you get only ones here, because also, of course, the 0.5 is interpreted as an integer. And you then, this is 0, it just takes the floor level, and then you add always 0 to 1, 1, 1, and so on, and then this array appears. So in this case, it would not make so much sense, I guess, but if we maybe do it in such a way, maybe 1.5, and we go up to maybe 20, and we run this again, then you see that now we increase it or increment it by 1, 1, 2, 3, 4, 5, because this is again interpreted as an integer, which means 1, and then we add 1 to 1, 1 to 2, 1 to 3, and so on. Okay, then we create another array, R3, and for that we will use now the function linspace. This is the other function that is very important to know, and here we have to also set an start point and end point, but here we have to then set the number of steps that we want to create. So in this case 20, and if we don't want to include the endpoint, we can write here endpoint false. And what we can also do, we can set another option, red step equals true, and this gives you another array where you can see the spacing, and this I want to show you now. So let's call it SP. Now there are 2 return values, one is the array itself, one is the spacing, but of course you can also ignore these 2 parameters if you don't need them. You can only insert these first 3 parameters. This I'm only showing now for educational purpose. Now you can print R3, and let's do it maybe below that, and when we run this, you can see now we have here a new array starting with 1, 1.45, 1.9, 2.35, just because this distance is divided by 20, and this gives then also our spacing, and this we have here in our saved and stored in our variable SP. And if we now run that with giving out SP, you see the spacing is 0.45, which you can also see here. So in some cases, especially when you want to loop over such an array, then it's important to know what is the spacing. Otherwise, you have to calculate this by yourself. So it's quite a useful thing to save time and to create less debugging problems for your code that you have written. So these 2 functions I would keep in mind because they are very important. Okay, what I also want to show is that you can either change the D type directly when you create this array. You can define this, or you can change it later. So for example, if we write here R3 equals R3, and then we use the function sType, and then insert here integer, and we print out now R3, and yeah, we run this, you will see that now we have only integers here. So all the doubles or floats which we have here are converted to integers. So if you have not done this in the beginning, or you could not do this in the beginning, then later you can change this at any time. So this is also a nice, interesting feature. Of course, now we have created the arrays, but we also want to access certain elements of our array maybe. And for this we have also several options. We can either use the normal standard indexing in Python. So we could write, for example, R3, and then let's suppose we take the fourth element of that. And when we run this, you see now it gives you out a 2, which is here this value here actually. Or what we can also do, maybe I should disable this this help. Now what we can also do, we can write, for example, print R3 minus 1. And now we can run this, and again we start from the end here and go 1 in negative direction, which is a 9. So this 9 is now shown here. This is also a quite useful thing. And now you can do something which is called array slicing. This is a NumPy feature. So if you write, for example, print R3 and then for example 5:10, and you run this, you will see now you get another array here, which is containing only the items from item number 5, which is 3, to item number 10. So 3, 3, 4, 4, 5. These 5 items are now shown here. So this is a very simple thing, and I think much faster than writing or making a list in Python than writing a for loop, looping over this. So this is a really beneficial tool, and you can create sub arrays by defining this as a new array. Then you get a new array with containing only these 5 elements. So it's a very powerful thing. And you can do, of course, much more with this. You can also write, for example, A3 5:10, 2. And when you run this now, you see that you get only 3. And the reason is that the last one gives you the spacing. So you jump over every second item. So this is also a very nice thing. Or what you can also do, for example, and this feature I like a lot, you can write R3 and then, for example, 5 : and when you run this, you see now it starts with 3, which is the 5th one, and goes up to the end. So when you leave the last item blank, empty, then it goes until the end of this array. And of course the same we can also do, for example, by writing :10, and when we do this, then you can see it goes from 1, or from the first entry up to the 10th one. It's also a very nice feature actually. Okay, now we have created a few one-dimensional arrays. Now I would like to explain how you can call a two-dimensional array, and now for this we call it maybe R2D. And then again we use the same command, the same function array. And again, we insert some random values, but we have to now keep in mind, instead of only making one rectangular bracket, we have to insert 2. So now let's suppose we create here 3, 5, 8, 1, 3. And then here we insert another list. So 12, 16, for example, 13, 18, 15. We want to keep the dimensions in both directions, x and y, equal, so I'm writing it in such a way. But you can also play around with this as usual and see what happens. So now we can print out our array, print R2D, and you can see now we have here our two-dimensional array, which with all the entries that we have included here. Another important possibility is to also give out the dimension. So you can write, for example, r2d.dim, and this gives you out an integer, and this is 2, Yeah, so we have a two-dimensional array, a matrix, you can say, with the dimension 2, because we inserted here 2 lists. And what is in this case more important to know, I think, because when we want to do some matrix manipulation, we have to know how many rows and columns we have. So this we use shape. So shape actually gives you here the number of rows, which is 2, and then the number of columns, which is 5. So we have 2 columns. We have 2 rows, but 1, 2, 3, 4, 5 columns. So this is a very important thing to know. So now in the next step, I want to show how you can also reshape a matrix. So for example, if you write here R2D dot shape equal 5, 2, the opposite of what is shown here, and then you print R2D and you run this, you see that now from this horizontal matrix that we created here, we created now this vertical matrix. So now we have 2 rows and 5 columns. And now of course you can do many things with two-dimensional arrays. One thing which I want to show is maybe how to flatten them. So you can convert this two-dimensional array into a one-dimensional one. This can be sometimes important, especially when it comes to plotting. This conversion of an array into a one-dimensional vector is always an important thing. So for this you can maybe we create another matrix here, which another array which we call R2D flat, and then we use the built-in function flatten. One can also order it in different way, but I don't want to go so much into details at the moment. And then you can print out R2D flat. And when you give this out, now you can see all the entries that we created are given out in one array, in a one-dimensional array. Very nice feature. You can do this also with three-dimensional arrays and so on. And there are use cases for that, but at the moment, as I said, I don't want to go so much into detail. Now, one strength of NumPy is how to store arrays into text files if you want to use them later in another program, for example, or just saving them on the disk. So for this, there is a function which is called save txt, save text, and then we create a text file. Let's call it maybe num.txt or maybe CSV for comma separated values and so on. And then we have to insert our array that we want to store, and we call this then maybe R2D. And if we do this and run this program, you will see you get now here a new text file, and it just stores all the values that we created as doubles or as floats, just because we have not defined the type as an integer. So otherwise it would only show the integer values. Now it shows a lot of zeros also there, but it doesn't matter. It's just for the purpose of explaining how it works. And then of course we can also load it back. So maybe we call this new array that we want to create R2D load, and we write here np.loadtxt. There's also another function available, but I don't want to explain this now. So we can write now np-load text, and then of course we have to insert here our num.txt, and then it automatically creates an array, this two-dimensional array, and we can print this out, R2D load, to prove that it works. And when we now give this out, you see now we have the same array that we created before, even here shown directly as floats, because it automatically loads this as floats. Okay, it is perfectly okay. Everything is working very well, and this is another important feature, as I said. So now let's come to some very important tools. When it comes to matrix manipulation, as I said, this is a very powerful tool, NumPy, for doing everything or most of the things related to linear algebra, if not everything. So for example, we could easily multiply two matrices with each other. So for that purpose, we multiply maybe R2D with itself, and we write here this asterisk R2D. And if we print this out, you can see now instead of 3, we have 9. Instead of 5, we have 25. So what it does actually, this operator here, is that it multiplies every value of this one array with with the same value with the same column and row index of this second matrix that we include here. Yeah, so in this case, of course, it's just the squared value because we use the same arrays, but you can also we can also multiply one array with another one. Okay, what we can also do, what is maybe nice to show is that we can add two arrays with each other. Yeah, so R2D plus R2D. And now we have here 3 plus 3 is 6, 5 plus 5 is 10, and so on. So this also works quite easy. And as I said, if you do this in built-in functions in Python, it's much more time-consuming. These operations are less performant, so this is the best way how to do that. And yeah, and then there's another one, the so-called dot function, which is included in NumPy. And here in this case, yeah, we can just write maybe R2D, comma R2D, so it calculates the dot function of these two matrices. If you have vectors, it's just the scalar product, the dot product, and it gives you a number. Here in this case, it's the matrix multiplication. Yeah, so it really multiplies this matrix with this one here. And when you run this, you will see you should get an error message here because you cannot multiply 5, 2 with a 5, 2 matrix or 5 cross 2 with a 5 cross 2 matrix. As you learned maybe in school, yeah, you have to transpose the first one. This is not done automatically. You have to do this manually. So now here the number of the rows and columns are changing actually. And then at the end you get a 4 cross 4, 4 times 4 matrix with these entries here. And you can do this also by hand and check whether you get the same results, but I think the multiplication should have been done correctly. Yeah, so it's really a nice feature. So now, if you do things with matrices, you come also maybe after some time into the in the condition that you have to create some empty matrices with only zeros or with ones, or some identity matrices. So what we can do now, there are built-in functions in NumPy, which one is called ones, and we can write, for example, 3.3 or 3,3. And when we run this, you see, here, if we want to do this, we have to use double parentheses. This is very important. I'm also forgetting this all the time, but otherwise it will not work. It will give you an error message. And now you can see you create a 3 times 3 matrix or 3 cross 3 matrix with only ones. Yeah? And the same we can do also with zeros. This is as simple as that. So here again we get a 3 times 3 matrix with only zeros. And the one which is also important is identity, and in this case, of course, we should only insert here one value, yeah, because it has to be a squared matrix. And now you see you get here everywhere zeros except on the diagonal. Yeah, so this also works quite well. And now you could do some matrix manipulation with these ones. Okay, these are in principle the most important functions that you should know when it comes to NumPy. But there's another thing which I would like to explain regarding random values. And this is because it's very powerful when it comes to the creation of certain random distributions, for example, normal distribution, Poisson distribution, binomial, and so on. And for that, I just want to show how it works. So before we can do this, we have to insert another package which is called a random, and this we have to import. From NumPy import random, and this is very important. Because this random package of Python does not help us. We have to use it from NumPy, otherwise it will not work. So x equal random, then binomial. This is the name of the function that we want to use, and then we have to define the number of n. As you know from binomial distributions, we have to define the probability. Let's suppose we call that, or we give a value of 0.5. and we have to create a size of our sample. Yeah? We could start with maybe 10, and if we print out x, now it just throws a dice actually 10 times, and now we get here values from with a probability of 0.5. And this is quite simple, and we can also increase this. So let's suppose we do this 1000 times. It will give you all the values here out. It's not a dice because of the probability that we have chosen, so you also have values here of 7 or 8, but it's just to show how binomial distribution works. And now the most important thing is that we can plot this now easily, as I have explained this before. So we could write plt.plot x, and then we can also save this figure as maybe binomial.png. And when we run now our code, as you can see, we get now here our PNG binomial. This is of course stupidity what I have done now, because we don't want to actually plot it. We want to histogram it. So we use the function hist from PLT. And now we do it again. And now it should work. And now you can see here that we created our histogram. There's still this the function that we have plotted before included. So of course we should, before we do that, write here plt close. So the previous plot is actually deleted. And now if we do this now, we can see only this histogram here, including our binomial distribution. And this you can do with, you can test this with other distributions, whatever comes to your mind. And then it gives you a lot of nice possibilities to really do a lot of stuff with NumPy. Okay, and with this I want to stop now this very short introduction into NumPy. And as I said, if you are interested, put it into the comment section, then I can maybe make a tutorial series about that whenever I have a little bit time. And I hope you enjoyed the video. If you like it, please hit the like button. As usual, subscribe my channel if you have not done so far. And hopefully see you soon for another Python video.